Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. And in this video, we are going to finish out our discussion on the fundamental theorem of algebra. And this assumes that you have watched all the videos in this series up to this point, including the video on just an introduction to the fundamental theorem of algebra, the video on the complete factorization theorem, and the video on the zeros theorem and the conjugate zeros theorem. In this video, we're going to go ahead and use the fundamental theorem of algebra, and unfortunately we just have one little last theorem to prove here, so you should get the feeling that, man, there are a lot of theorems in this section. Well, with a name like the fundamental theorem of algebra, you gotta figure there's a constellation of theorems that kind of revolve around it. It's going to be very important that we spend our time building our theory first, so that when we use the fundamental theorem of algebra, it ends up being very powerful for us. We'll have a lot of ways we can use it. So on with the show. Using the fundamental theorem of algebra, we arrive at our final theorem, the linear and quadratic factors theorem. This is actually just a slight extension, a combination of two theorems really, which one is the complete factorization theorem and the other is the conjugate zeros theorem. And this just tells us that every polynomial with real coefficients can be factored into the product of linear and irreducible quadratic factors with, well, real coefficients. We faced this style of theorem before where it's not an if-then statement. It doesn't explicitly state if this is true, then that is true. However, it is an if-then. If we have a polynomial with real coefficients, then it can be factored into the product of linear and irreducible quadratic factors with real coefficients. So we're going to start by supposing that P is a polynomial with real coefficients. And we're also going to mention that since real coefficients are complex valued coefficients, we can use the complete factorization theorem here. I should tell you that C sub I, they are complex numbers, not just real numbers, but a bigger version of real numbers. They could have imaginary parts with them. However, we have the conjugate zeros theorem, which tells us that not only do complex conjugates come in pairs, which tells us that any complex valued zero comes in a conjugate pair. That is, anytime that you have a zero that has an imaginary part to it, it will come in a pair. And here I just labeled them Z and then Z bar for its conjugate. Those both must be zeros. If you have a zero with an imaginary part, a non-zero imaginary part, that is. This means that you have two factors. If you have complex valued zeros with non-zero imaginary parts, you have two factors that are of the form x minus z and x minus z bar in this list of factors right here. Now I do want to mention before we go any further that complex zeros theorem only works if you have real coefficients on your polynomial. That's critical, because if you don't have real coefficients on your polynomial, you cannot use the complex zeros theorem. And that ends up being a little bit of a sticky part for some obscure examples. So I just wanted to mention that here, that's the only reason why we know we have complex conjugates as the zeros, is because our coefficients of our polynomial are real numbers. Now remember our goal. Our goal is to say that this polynomial can be reduced into the product of linear and irreducible quadratic factors, each of which have real coefficients. Right now we know we can take that polynomial and factor it into the product of linear factors, but some of those coefficients might be complex valued with non-zero imaginary parts. But what we're saying is, well, if we take those ones with non-zero imaginary parts, let's go ahead and multiply them together and see what we get. Remember, z here is a plus bi, and z bar, which is the conjugate, is a minus bi. If you multiply those out, you'll get x squared minus a plus bi times x minus a minus bi x, and then finally plus a plus bi times a minus bi. There we go. That's the distribution. And now we'll go ahead and collect like terms here. X squared, everything that has an x attached to it, I'll group up. So I have a negative a minus another a. So I'll go ahead and write that as, I'm going to write it this way, plus a negative 2a. And then I have a negative bi plus a bi. Well, that's kind of convenient, right? Negative bi and then plus a bi, those cancel beautifully. And now I'll write plus, and then I'll multiply all this binomial stuff out here. A squared plus b squared I squared. Remember, I squared is negative 1. So this ends up being x squared minus 2ax plus a squared minus b squared. And I just realized this part right here should be a minus. That was my bad. Sorry about that. So I squared is negative 1, so this become a plus. I just looked at that and thought, wait, there's something weird about that. All right, so we got that fixed. Now let's go ahead and take a look at this resulting expression. This is a quadratic, and the coefficients of this quadratic, 1 on the x squared, a negative 2a on the x, and then the constant being a squared plus b squared. There are no imaginary parts. This is a quadratic with real coefficients, and we would call this an irreducible quadratic over the real numbers, because if you tried to factor this, it would factor, as we have just derived it, into the product of linear factors with imaginary parts. And so that will not factor over the real number system. It factors over the complex, but not over the real number system. And as such, we would call this quadratic at the bottom an irreducible quadratic. And that actually proves this theorem. We now know that we have a polynomial. We started with a polynomial with real coefficients. And then we knew that that could be factored into the product of linear factors with complex valued components there. But if we knew that we had a complex valued component or complex valued 0 with non-zero imaginary parts, that they come in conjugate pairs because of the conjugate zeros theorem, and we can use that because our polynomial has real coefficients. So we looked at those factors with conjugate pairs, and we said, well, if they come in pairs, let's go ahead and multiply a pair together and see what happens, and we get an irreducible quadratic, which tells us our polynomial will be the product of linear factors with real numbers and irreducible quadratic factors with real coefficients. So we now have what we need to do anything we want within reason with polynomial expressions, functions, and equations. So let's go ahead and find all zeros, both real and complex, for the polynomial p of x is equal to x to the 6 minus 1, and factor it completely. So prior to this, you might have been asked just to factor this, maybe in an Algebra 2 class actually. And in an Algebra 2 class, you could factor this pretty easily. It is a difference of cubes or a difference of squares, however you want to visualize that. You don't have to use synthetic division here. Just note that this is actually a difference of, for example, squares. So this is a good example of doing something a little overboard. If you think that you have to always use synthetic division to arrive at the factors, you don't. If you can see that it is a difference of cubes or a difference of squares, do that. I will go ahead and continue the factorization process here. And that's just using the sum and difference of cubes factorization formulas that you should know from your Algebra 2 course. And now we need to factor that x squared plus x plus 1 and the x squared minus x plus 1, mainly because those two should be able to be factored. Right now, we have completely factored the polynomial into the product of linear and irreducible quadratic factors. So we've arrived at that last theorem, basically. But we know that we can factor a little bit further if we allow ourselves to factor over the complex numbers, which we'll go ahead and do. Note those two highlighted trinomials there. When you use a sum or a difference of cubes formula, the trinomials you get in the end will be prime, or in other words, irreducible quadratic polynomials. You can still factor them though, just use a quadratic formula. So I'm going to go ahead and off to the side here, use a quadratic formula. So for the trinomial x squared plus x plus 1, using the quadratic formula, we get that x is equal to -1 plus or minus the square root of 1 minus 4 all over 2. That reduces significantly to be 1 plus or minus the square root of, well, I'll just say I times the square root of 3 all over 2. You should write this in standard form being -1/2 plus or minus square root of 3 over 2i. That's the standard form for a complex number. It's just better to write it as the real part and the imaginary part. And then you move everything over to the left side. So if there was a plus there on the square root, you would have the factor x plus 1/2. And then remember, if it was a plus on the square root, then you would subtract the square root of 3 over 2i. And the other factor would be, again, if you had a minus on the square root of 3 over 2, you'd have x, again, plus 1/2, but then you would add square root of 3 over 2i. And so that would be the factors for this, which I'll write in once I'm done factoring the other one. And the other one actually is very similar. In fact, you can almost steal the entire computation here from the first one, because the only difference is going to be it's a positive 1/2. Otherwise, it's still going to look like this. So there's no real huge difference. Plus or minus root 3 over 2i. So you can see that essentially it's going to be the same two factors with minus signs in front of the 1/2. You can double check that, but that is true. So I'm going to go ahead and write out the full factorization here. This is equal to, we have an x minus 1. And then our factors were x plus 1/2, and then minus root 3 over 2i, and x plus 1/2 plus root 3 over 2, again I. Then we had the x plus 1, and you can see I'm beginning to run out of room, so I'm going to just loop up this stuff right here and move it over, get it out of my way, and finish this out. This is going to be x minus 1/2 minus root 3 over 2i, and x minus 1/2 plus root 3 over 2i. That is the complete factorization of x to the 6th minus 1. And it did say, by the way, the problem did say find all zeros. So I suppose that I should state the zeros. Not that it's that much more challenging now that we've already factored. But the zeros are x equals 1 from the very first piece right there. I'm going to go ahead and take care of this one as well. So I'll just say x equals plus or minus 1. And then I'll go ahead and start with these two right here. X equals, there are a few ways you could say this. I'm just going to do it this way. Negative 1/2 plus or minus root 3 over 2i. That's what we got from the quadratic formula. And then the last one is x equals positive 1/2, again, plus or minus root 3, again, over 2i. Those are all 6 of our roots for the 6th degree polynomial. Remember, the degree of your polynomial will tell you how many roots that you have altogether, and that's including complex valued roots. Now, this is kind of a wrap up of all the different things you could possibly see when you're working in a section that's dealing with the fundamental theorem of algebra. Very common that somebody just starts handing you information about a polynomial and asking you to build that polynomial. So find a polynomial with integer coefficients that satisfies the given conditions. U has, so they're telling us that the polynomial has name U. U has degree 5. The zeros, and I'm going to write these down actually because this ends up being somewhat important to write in a list. So the zeros and their multiplicities. So they tell us it has a 0 at 1/2, has a 0 at -1, and a 0 at -I. And has a lead coefficient of 4. Okay, well, that will be important later. The 0 of -1 has multiplicity 2, so I'm going to write 2 right there. Well, this tells us actually all the zeros, because if -I is a 0, then positive I is also a 0. Each being zeros of multiplicity 1. So 1 plus 2 is 4, plus this one right here is going to be 5. Again, complex zeros come in pairs. And so now we can build our polynomial. They titled it U. I'm going to assume it's of x. We do not know the coefficient, but we know the zeros. X minus 1/2 will be a factor because 1/2 is a 0 of multiplicity 1. X plus 1 squared is a factor because x equals -1 is a 0 of multiplicity 2. And now let's deal with the conjugates, or I'm sorry, with the complex numbers. So x, let's deal with the minus I here. So if x equals -I is a 0, then x minus a -I is a factor. So that means that x plus I. And if positive I is a 0, then x minus that I is a factor. That's kind of nice. We have that all set there. And now we just need to know what this polynomial becomes. We have one other piece of information, that the lead coefficient should be 4. Now, right now I can tell you that that just means a equals 4. And why that is true is because when you multiply all this stuff out, x times x times x times x times x will get x to the 5th, but with a 1 in front of it, because all of these coefficients are 1s. Well, if I want that to be a 4, I better force a to be the number 4. But you could do this a different way as well, and I think it best to show you both. So again, the easy way to do this right now, because we know the leading coefficient right here, they're telling us has to be 4. And if you had multiplied this entire polynomial out, you would get 1x to the 5th and a bunch of other stuff. And of course, you're going to multiply all that stuff by a in the end. And so you know immediately, okay, well then that means a has to be 4, because I have a 1 in front of my x to the 5th multiplied by a, so it's ax to the 5th, so obviously I'd like a to be 4. But what if I didn't tell you that the leading coefficient had to be 4? What if I told you that the coefficient of x cubed had to be 4? Well, how would you do that? That's where you invoke kind of the bigger method. The bigger method is really to keep this a hanging out front and then just start multiplying everything out. So this is going to be an x minus 1/2. I'm not going to multiply that first, but I am going to square this x plus 1. That becomes an x squared plus 2x plus 1. I'm also going to multiply out this x plus I times x minus I, which is going to be an x squared. Let's see, minus xi plus xi, so they cancel, minus I squared, but I squared is a -1, so it's a plus 1. So quickly, it kind of compresses down to that. I am probably just going to multiply the two binomials You don't have to multiply the two binomials, but I'm just going to. So if you don't like how this is going to work, I'm sorry. You can multiply any other way you wish. I just like to multiply binomials first. Grab these guys and kind of showcase where my brain is going. And in fact, let me make a little space there. So let's see, I have a, let's see, x times x squared is going to give me an x cubed. X times 1 is going to be a positive x. A negative 1/2 times x squared is a negative 1/2 x squared. And finally, a negative 1/2 times 1 is a negative 1/2. And we still have this trinomial x squared plus 2x plus 1 hanging out. And now we're going to go ahead and multiply through. Again, this is going to be, actually, you know what I'm going to do? I'm going to rewrite that in descending power order, just because I think it's nice to do that. So let me just kind of clean this up really quickly. And now I'll showcase my multiplications here. I'm going to multiply x cubed against each of these pieces. And you know what? I'm actually going to, because I can, I'm going to showcase a different method of multiplication. You may have seen this before, but if you haven't, you'll be happy to see it, I think. So if you write out that polynomial, x cubed, was it minus 1/2 x squared, and then plus x and minus 1/2, and you stack below that the second polynomial, x squared plus 2x plus 1, you could treat it like a multiplication problem from when you were in an arithmetic class when you were a child. So if you took 137 and multiplied it by 43, you would say, okay, well, 3 times 7 is 21, carry the 2. 3 times 3 is 9, plus 2 is 11, so carry the 1. And 3 times 1 is 3, plus 1 is 4, right? And then you would put in a placeholder and say 4 times 7 is 28, carry the 2. 4 times 3 is 12, plus 2 is 4, carry the 1. And 4 times 1 is 4, plus 1 is 5, and then you'd add the stuff up. So remember that process from when you were a child. You will do the same thing here. It's actually fairly convenient. 1 times a negative 1/2 is a negative 1/2. 1 times x is just a positive x. 1 times a negative 1/2 x squared is a negative 1/2 x squared. And 1 times x cubed is a positive x cubed. Then you move to the next space right here. And we say 2x times a negative 1/2 is a negative x. Notice how I have a placeholder in a way, right? 2x times x is a positive 2x squared. 2x times a negative 1/2 x squared is a negative x cubed. And 2x times x cubed is a 2x to the 4th positive. Then you go to the very last one. Again, you'll have a couple placeholders here. So placeholder, placeholder. And x squared times a negative 1/2 is a negative 1/2 x squared. X squared times negative 1/2, I'm sorry, x squared times x is a positive x cubed. X squared times a negative 1/2 x squared is a negative 1/2 x to the 4th. And finally, x squared times x cubed is a positive x to the 5th. And then you can do the same thing you would do in arithmetic. You would add these up. Let's see, negative, so that's negative 1, so this is a positive x squared. Let's see, there's a positive x cubed. Add these up. This is a positive 3/2 x to the 4th, and finally we have x to the 5th. So that's a kind of a cool way to multiply things out and keep it clean. And you'd write a x to the 5th plus 3/2 x to the 4th plus x to the 3rd plus x squared, and finally minus 1/2. Now, again, from the get-go, I had said that really, because we wanted the leading coefficient to be 4, it was obvious that a was going to be 4. But what if I told you that I wanted the coefficient of x to the 4th to be 4? Just for giggles, let's just pretend, as an aside, What if we wanted the coefficient of x to the fourth to be 4? Now remember, we're pretty much done with this problem, by the way. If you let a equal 4 here, you get 4x to the fifth plus 6x to the fourth plus 4x cubed plus 4x squared minus 2. Okay, that's done. But if you wanted not the leading coefficient to be 4, but the coefficient of x to the fourth to be 4, then you need a times 3/2 to be 4. Simple problem, just multiply both sides by 2, and divide by 3. So that would imply that a would have to be 8/3. And then you would go ahead and distribute that through. So that's just a piece of information that if it's not always the leading coefficient, you're going to have to do something like this in the end, really minor. But once you know that a is 8/3, you just then distribute 8/3 to each of those pieces. Nothing big, but I'm just letting you know that's how that would be done. Now let's make sure that we are completely finished with this problem. Find a polynomial with integer coefficients that satisfies the given conditions. Okay, we did. We're good. Now, as a final example in this material, because we've done factoring over and over again, so I just didn't want to do a ton of factoring, but we're going to show that these two complex valued numbers are both solutions of that equation right there, but that their complex conjugates are not. And this will seem counterintuitive to a lot of people. So let's just do the 2i. We don't have to actually do both of them. We can just do the 2i, right? Because talking about 2i is just enough. All right, so let's go ahead and plug in 2i. If you allow x to be 2i, you get the following. 1 plus I times 2i, and then plus 2 plus 2i is equal to 0. And you're just checking this. They're just telling you, hey, show that these are both solutions. So let's just check that 2i is a solution. We're not going to check the other one. And so 2i being squared is actually a negative 4, right? Because that's 4 times I squared, which is negative 1. Minus, let's go ahead and distribute that 2i through. So minus 2i and minus I times a 2i is a minus 2i squared, but remember I squared is a negative 1, so it's a plus 2, and then plus 2 plus 2i. When you group all that information up, let me just say, is that 0? You get negative 4 plus 2 plus 2, and you have a negative 2i plus 2i. The question is that 0? And the answer is heck yeah. Now let's look at the conjugate. They're saying, guess what? 2i is a solution to that, and we've shown that. Sure. Show that the complex conjugate is not. Well, what is the conjugate of 2i? Well, the conjugate of 2i is negative 2i. That's the conjugate, right? Because 2i is 0 plus 2i, so its conjugate is 0 minus 2i, or a negative 2i. So let's go ahead and take a negative 2i, plug it in, and I'm just finishing this out here. And I put a question mark. Is that equal to 0, actually? Well, let's see. Negative 2i squared. That's going to be 4 with a I squared, or a negative 4. So far, so good. Distribute this negative. Let's see. I'll do a negative times negative 2i. So it's a positive 2i times 1. And a positive 2i times I, which is a minus 2. Okay, so far, so good. And then plus 2 plus 2i. Again, we're asking, is that 0? Well, let's see, negative 4 minus 2 plus 2 is a negative 4. 2i plus 2i is a positive 4i. Is that equal to 0? Well, I think you all agree it's not equal to 0. And why doesn't this violate the conjugate zeros theorem, right? Because the conjugate zeros theorem says that we should get, if we have something that turns a polynomial into 0, and if that something is a complex number, its conjugate should also be a 0. But that's actually not what the conjugate zero theorems says. Recall from our previous lecture, the conjugate zeros theorem says that if the polynomial has real coefficients, that real coefficients, I made a big deal about it because it's incredibly important. You can use this theorem if your polynomial has real coefficients. However, the polynomial we were just dealing with does not have real coefficients. So the conjugate zeros theorem is not applicable to this situation. And that's what I've written here. Since the polynomial doesn't have real coefficients, the conjugate zeros theorem doesn't apply. So all bets are off, basically. So if somebody said, I have a solution 1 minus I that they state above, you cannot guarantee that 1 plus I is also a solution because the coefficients are not real numbers. All right, so that rounds out our entire conversation about the fundamental theorem of algebra, the complete factorization theorem, the zeros theorem and the conjugate zeros theorem, and then the linear and quadratic factors theorem. Quite a few theorems in this one single section, but it's super important. And the punchline is this, basically. Given any polynomial, you should be able to factor it completely over the real numbers into a product of linear and irreducible quadratic factors. And again, that's because of the theorem we started with in this video. That's kind of the punchline of everything. Now, if you're dealing with a course that also deals with complex numbers, then you know by the fundamental theorem of algebra that you can continue that factorization process until you get to the product of linear factors with complex number coefficients. And so this is really kind of the end-all be-all of this section. I hope that it wasn't too terrible. That's kind of one of the humps in a pre-calculus course. So once you've made it through this, it's smooth sailing for a little bit.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.